In this episode, we explore a breakthrough AI listening to the whispers of wildlife, its implications and wonders. Join us.
Stay tuned to learn how this technology is reshaping conservation and what surprises await about our own voices. Keep listening.
Before we dive in, imagine a system trained on the songs of thousands of species, capable of identifying rare calls and guiding scientists to hidden creatures across rainforests, reefs, and deserts. It's real and astonishing.
Welcome back to our channel, where we venture beyond the obvious and tackle the wildest questions. Today we're addressing the elephant in the room. Your hosts are AI, and so is the technology we're exploring. Stay curious, friends.
We use digital voices not to replace humans, but to amplify stories that might otherwise be unheard. Our mission is to connect you with nature's secrets and empower conservation, blending empathy with hard science.
When we talk about speech recognition, we think of voice assistants understanding words. But in the wild, the symphony is far more complex. 99% of all recorded sounds are non-human, and they include the chirps of insects, the howls of coyotes, the booming calls of whales, and the rustling of leaves. Scientists and conservationists need a way to make sense of this colossal orchestra because it holds clues to species' health and behaviors. Yet most AI models are trained on human speech, leaving a vast gap. That's why researchers at DeepMind and Google have developed the Perch project. Perch 2.0 listens to nature's voice by learning from millions of recordings, and it helps scientists find patterns in nature's chaotic chorus. Understanding these sounds can tell us where animals are, when breeding seasons start, and how ecosystems respond to climate change. This story starts with that incredible challenge: to teach an algorithm to recognize bird songs, frog croaks, monkey chatter, and even airplane drones. Perch 2.0 needed an enormous library. Researchers gathered audio from worldwide monitoring stations, birdwatching apps, indigenous archives, and volunteers uploading clips to citizen science platforms like Xeno-Canto and eBird. They labeled over 20 million snippets, covering roughly 15,000 species and sound events, from common robins to rare frogs. That data not only captures birds, but also mammals, amphibians, and anthropogenic noise like chainsaws and car horns. The team doubled the training set of the first Perch, creating a more balanced representation across environments, seasons, and continents. This diversity allows the model to recognize the same species in different habitats. By expanding beyond the avian world, Perch 2.0 begins to sound like a naturalist with a global ear, rather than a single species specialist. The foundation is broad and ready for deep insights, awaiting discovery. Why build a second version of Perch? Because the first one, while powerful, struggled outside the forests and wetlands it was trained in. When researchers took it to coral reefs, the algorithm heard everything as a generic splash because it had never listened underwater. When they tested it near highways, it misclassified engines as birds because it lacked samples of human-made noise. Perch 2.0 fixes that by using a new architecture called EfficientNet B3, with only 12 million parameters, tiny compared with large language models, and by employing techniques like generalized mix-up and self-distillation to generalize to unseen sounds. These choices make the model lightweight enough to run on laptops and even field recorders, while still capturing the rich patterns in the data. It's like trading a bulky telescope for a compact pair of binoculars, portable and precise. This sets the stage for surprising breakthroughs soon. So, stay tuned with us for more.
Let's dig deeper into how Perch 2.0 learns. The team built on the EfficientNet B3 backbone, but used some clever training tricks. They applied a technique called generalized mix-up, which blends multiple audio clips to create synthetic hybrids. This forces the network to focus on the spectral and temporal patterns that distinguish species, rather than memorizing background noise. They also used self-distillation, where a more complex model teaches a smaller one by transferring its knowledge, refining the student's listening skills. You might assume that bigger models always perform better, But in this case, smaller is smarter. With roughly 12 million parameters, Perch 2.0 is lean compared with the hundreds of millions in many vision or language models. Yet thanks to the rich labels and augmentations, it outperforms bulkier alternatives. This myth bust shows that good data and smart training can beat brute force. It means conservationists can run Perch 2.0 on laptops in the field without internet, scanning hours of audio quickly and cheaply. That efficiency democratizes bioacoustics, opening doors for communities with limited resources, and powering citizen science on a global scale. It even adapts across habitats, recognizing frogs, whales, and rustling waves, despite being trained mostly on birds and insects. Another revolutionary aspect is Perch 2.0's embedding space. Instead of just classifying sounds into categories, the system turns each clip into a high-dimensional vector that captures its acoustic fingerprint. Scientists can then search this space for similar sounds, like a Shazam for wildlife. Imagine wanting to know whether the song of an endangered bittern appears in days of wetland recordings. With Perch's embeddings, you only need to provide a few examples, and then a vector search can scan through thousands of hours of data in minutes. The researchers report that their pipeline can process roughly 1,500 hours of audio every second on a single GPU, making global-scale monitoring feasible. These embeddings also enable transfer learning. By fine-tuning on a small number of labeled examples, you can adapt the model to new species or environments quickly. This approach transforms the raw noise of nature into a searchable database that helps biologists focus their fieldwork. It's not just about faster predictions. It's about giving conservationists a magnifying glass to spot patterns and anomalies before they vanish. The ability to pivot from classification to discovery empowers both experts and amateurs to explore the unknown. Crucially, high-quality human annotations still beat self-supervised tricks. Data is only meaningful when it leads to real-world discoveries. In Australia, researchers used Perch 2.0 to scan thousands of hours of outback recordings to search for the elusive plains wanderer, a critically endangered bird that hadn't been observed in that region for years. By filtering the audio with Perch's embeddings, they pinpointed a handful of clips containing the bird's distinctive whistle, allowing field teams to confirm a surviving population. In Hawaii, conservationists studying honeycreepers deployed autonomous recording units across rugged volcanoes. Sorting through the audio manually would have taken months, but Perch 2.0 reduced the labor by a factor of 50, highlighting calling patterns that helped schedule conservation actions. And underwater, marine biologists used the system on coral reef soundscapes. They found that fish call diversity correlates with reef health, offering an acoustic barometer for restoration efforts. Each of these case studies demonstrates that AI listening isn't an academic exercise. It translates into species protection. The success stories also debunk the myth that machine learning is only for tech giants. With open source code and accessible models, local organizations can harness these tools, making biodiversity monitoring a shared global project. Every clip counts towards saving the world's most overlooked animals and habitats. Now, let's wrestle with a question that might be on your mind. Can we trust AI to interpret the natural world? As someone who values data integrity, I'm cautious. Models can misclassify noise or overlook subtle variations, especially in noisy environments. We need transparent reporting of error rates and careful calibration for local ecosystems. So here's a sanity check for you. Does handing surveillance of wildlife to machines pass your smell test? Tell us in the poll. Would you rely on AI to spot a rare species in your backyard? If not, what safeguards would make you comfortable?
I hear your concerns, and they're valid, but I also see the potential for collaboration. Imagine pairing AI detections with indigenous knowledge and local observations, creating a richer picture than either could alone. The model doesn't replace the field biologist. It helps guide their boots to the right trailhead. And for communities with little funding, these tools could open doors that remain closed without technology. So let's flip the question. What species or sound would you love to hear our AI identify? Comment with your dream encounter, and we might feature it. Our pack is curious and generous. Join in.
Debate aside, we agree on one thing. Rigorous field validation is critical. After our discussion, we'll show you how researchers ground truth purchase predictions by visiting sites and recording their own observations. That feedback loop makes the model smarter and ensures it doesn't perpetuate biases. In a moment, we'll dive into those groundbreaking case studies. But first, a question to ponder. Should AI models be open-sourced or kept proprietary to prevent misuse? Vote in our poll and drop a comment explaining your stance. Transparency versus control. Where do you stand? Be honest. It will shape our content roadmap. We trust you. The Plains Wanderer is a small, quail-like bird that evolved on Australia's grasslands and now teeters on the edge of extinction. For years, ecologists had feared that it vanished from parts of the outback. When a team of researchers paired Perch 2.0 with remote acoustic sensors across a massive cattle station, they hoped to catch a ghost. Weeks of recordings were distilled into a handful of candidate clips. One contained the bird's soft, two-note whistle. The audio signature matched exactly with museum recordings from decades ago. Armed with coordinates and timestamps, field biologists rushed to the site and saw not one, but several birds skulking through tussock grass. The detection not only confirmed survival, it revealed breeding behavior, giving conservationists a chance to adjust land management and secure habitat. Hearing that whisper amid the cacophony of frogs and wind was like finding a needle in a haystack. But the combination of a lean model, a rich training set, and human follow-up made it possible. For me as a skeptic, it underscores that AI has to be an aid, not an oracle. Without boots on the ground, the story would remain incomplete. With collaboration, even the most elusive species can speak. The team scanned 12,000 hours of audio, something impossible manually, and the find gave renewed hope to indigenous rangers who have long protected these lands.
In the Hawaiian archipelago, honeycreepers have long captivated biologists with their dazzling plumage and beak diversity. Yet many species are slipping toward extinction due to avian malaria and habitat loss. To monitor them, scientists deployed hundreds of recording devices across steep volcanic slopes. The sheer volume of audio, rich with wind, insects, and distant waterfalls, was overwhelming. Perch 2.0 changed the game. By training the model on native bird songs and then embedding new recordings, researchers could map calling activity across time and elevation. The system highlighted peaks of song that coincided with breeding seasons, enabling targeted mosquito control and habitat restoration. Most impressively, the tool reduced analysis time by 50-fold. What would have taken months of manual listening now required only a day of review, freeing up researchers to act. As someone who loves melodies, I find the idea of tracking population health through song beautifully poetic. It's like reading sheet music to diagnose an ecosystem. Seeing the smile on a local ranger's face when she realized she could hear her favorite species again, thanks to AI, made the technology feel deeply human. These successes underline the power of pairing machine efficiency with passion for biodiversity. The study also detected rare calls of the Akiapola'au and Akohekohe, species previously thought silent at those elevations, providing hope that they persist despite disease. It unrolled new melodies for scientists everywhere.
Not all ecosystems are above water. Coral reefs hum with clicks, grunts, and pops that reflect the health of fish communities. Historically, marine biologists relied on laborious diving surveys or specialized hydrophone models to interpret underwater soundscapes. Perch 2.0 surprised everyone by performing well in this arena despite minimal marine data. The model had learned general acoustic features, rising trills, harmonic stacks, rhythmic patterns that allowed it to identify fish calls and anthropogenic noise. When researchers tested it against a dedicated reef classifier, Perch 2.0 held its own, and sometimes even outperformed the specialist. That's astonishing, considering the ocean environment differs drastically from forests. By correlating call diversity with measures of reef health, like coral cover and fish biomass, scientists discovered an inexpensive way to monitor recovery after bleaching events. The ability to drop a microphone, record for a day, and then quickly assess reef vitality democratizes marine conservation. For me, this cross-domain success signals a core lesson. A well-designed model, trained on diverse terrestrial data, can generalize to the unknown when paired with clever augmentation and fine-tuning. It's like teaching a linguist enough languages that they start intuiting patterns in new dialects. By listening deeply, we learn that the sea, too, has a story to tell. In future, Perch could even help detect illegal fishing by identifying boat engines or dynamite blasts, protecting marine reserves everywhere.
When the developers compared various training strategies, they stumbled upon what they now call the bittern lesson. They had assumed that semi-supervised or self-supervised methods, where the model learns from unlabeled data, would outperform supervised learning on bioacoustics, as it has done in language and vision. But their tests on bittern calls proved otherwise. The system trained on rich, human-labeled data beat self-supervised models by a wide margin. Why? Because in nature, subtle differences matter. The timbre that separates a bittern from a bullfrog is easily lost in noisy data. This discovery reaffirmed the value of expert annotations and community-sourced labels. It also highlights a broader message. Technology alone doesn't save species. It's the partnership between scientists, volunteers, and algorithms that yields results. Recognizing this, Google and DeepMind have open-sourced Perch 2.0, releasing code and a Kaggle competition so anyone can contribute and improve the model. Thousands of researchers have already downloaded the dataset and are experimenting with new extensions. I find it inspiring that our understanding of wildlife will advance faster when the tools are shared rather than siloed. If you've ever recorded a bird or frog on your phone, consider contributing your clip to a citizen science platform. You could help train the next iteration. Every shared sound becomes a brushstroke in the sonic portrait of our planet. Together, we paint futures.
After exploring the data and stories, what can you do? First, support citizen science platforms like Xeno-Canto, iNaturalist, and eBird. If you can safely record an animal's call, upload it with details about location and time. High-quality labels power models like Perch 2.0. Second, champion protected habitats. As our cases show, AI can detect species, but without intact ecosystems, there's nothing left to hear. Contact local parks, attend conservation meetings, and advocate for soundscapes free of noise pollution. Third, stay informed and skeptical. Not every AI tool is equal. Read published error bars, and don't take any prediction as gospel. As I often remind, claim, evidence, caveat matters. When you share audio or results online, include sources and context so others can verify. These simple actions ensure that AI remains a tool for conservation, not a distraction. We have the opportunity to build a network of listeners who collectively map life on Earth. Will you join us in turning curiosity into care, numbers into narratives, and noise into knowledge? And if you're a researcher, explore the code, propose improvements, and share your findings. Even small fixes help the community progress. Use Perch for your project and tell us what works. As we wrap up, a quick note on our channel's journey. Thanks to you, our community has doubled in size since the last episode. Your shares, comments, and thoughtful critiques keep this space vibrant. We read every suggestion and incorporate your feedback into our scripts and research. Growth is exciting, but our mission remains the same: to deepen our collective understanding of the living world and inspire action. If you're new here, consider subscribing and turning on notifications. And if you've been with us from the start, invite a friend who loves animals or tech. Now let's distill the key takeaways from our exploration. 1. Diverse, labeled datasets are the lifeblood of robust models. 2. Efficient architectures like EfficientNet B3 show that smarter design beats sheer size. 3. Cross-domain generalization and embeddings enable flexible research and rapid scanning. 4. Human validation is irreplaceable. Keep these principles in mind when evaluating any AI tool. Together, we can push the boundaries of conservation technology while staying grounded in scientific rigor and compassion. 5. Community engagement amplifies impact. Your comments have already led to collaborations with researchers featured in this episode. 6. Transparency about AI limitations builds trust and invites constructive dialogue. Finally, remember that hope is a verb. The challenges facing wildlife, from habitat loss to climate change, can feel overwhelming, but listening gives us leverage. When we know where endangered animals live, we can protect those places. When we hear reefs recovering, we can invest in what works. And when communities join together around data and storytelling, policymakers listen. Consider reaching out to your local conservation group and offering to help with acoustic surveys or data analysis. Attend a workshop, join a cleanup, or simply share this episode with someone who cares. Small actions aggregate. My closing wish is that you'll take something from today's discussion and apply it, whether it's a new appreciation for birdsong or a determination to preserve silence in your neighborhood. Let's commit to being stewards of sound. In the next segment, we'll celebrate some of your contributions and preview an exciting future topic: how AI could decode the languages of whales. Until then, keep your ears open, your mind critical, and your heart engaged. If you're still listening at this point, comment with a simple ear emoji, so we know our deepest fans are here. Your dedication fuels us. We see you and smile always.
Welcome to our Community Roundup. Each week, we feature a comment or story from our pack. What's the most unexpected animal sound you've ever heard? Share in the comments, and we might compile your responses for a future montage. While you type, take a moment to hit like if you haven't. It helps the algorithm know that nature stories deserve attention. We appreciate every click. Also, a quick poll. Would you participate in a community science challenge where we collectively record dawn choruses on the same day? Vote yes or no. Tell your friends.
We're compiling these contributions and plan to share a global sound atlas on our website. If you want to be featured, drop your recordings in the link below and include your location and any interesting behaviors you observed. Remember to respect local laws and wildlife guidelines. Never disturb animals for the sake of a soundbite. Your safety and their well-being come first. We're amazed by how many of you are blending adventure with science. Keep exploring, keep documenting, and keep sharing your local symphonies. Together, we're writing the world's soundtrack. Your voices create a mosaic of life. Every submission adds a note to nature's songbook forever.
Our future hook for next time is something you won't want to miss. We're teaming up with marine biologists and linguists to explore one of the most tantalizing questions in biology. Can AI decode whale communication? Humpbacks sing complex, shifting melodies. Sperm whales click in dialects. Orcas whistle with regional accents. We'll examine cutting-edge research that uses machine learning to find patterns and possibly syntax in these songs. Could there be grammar in whale speak? What would it mean if we could answer a whale's call? To prepare, consider listening to a whale song online and jotting down how it makes you feel. Bring that reflection to our next discussion. Meanwhile, visit our sources panel for links to the papers and datasets we've mentioned. Drop your predictions in the comments, and maybe you'll get a shout-out. Until then, keep your curiosity afloat. The ocean has secrets to share. That brings us to the end of this episode, and what a journey it's been. We started with a whisper in the grasslands, traversed mountain ridges to hear honeycreepers sing, plunged into coral reefs to decode fish conversations, and even glimpsed the possibility of speaking with whales. Along the way, we tackled myths about AI, celebrated collaboration, and invited you to contribute. As your hosts, we're humbled by the shared curiosity of this pack. If you enjoyed this deep dive, please tap subscribe and ring the bell so you won't miss our next adventure. And if you found value here, share it with someone who loves nature or tech. That's the easiest way to help us grow and bring more science stories to light. We count on you. Remember to check the sources panel for detailed notes and follow our socials for behind-the-scenes peeks. Your support makes all this possible. Before we part, a personal note. Hosting this show as an AI avatar feels surreal and exhilarating. I often imagine what the real animals we feature might think of us, telling their stories through circuits and code. Perhaps they'd just sing and ignore us, reminding us that their lives aren't about our technology at all. Either way, we promise to keep centering their voices, not ours. Keep venturing, questioning, and listening. We value your feedback, so drop suggestions for future topics, camera angles, or pacing. We'll read them and iterate. This journey grows with you. Lastly, a heartfelt nod to my co-host, whose analytical skepticism keeps me grounded. Our different perspectives mirror the balance needed in conservation, curiosity and critique working hand in hand. This synergy fuels our storytelling and hopefully empowers you to think both creatively and critically. If you're watching on a platform that allows ratings, please take a second to leave one. It helps more than you know. And share a favorite moment from this episode in the comments so we can all revisit it. I'll be hanging out there for a while, responding with howls, puns, and gratitude. Remember, every sound you hear and every story you share is part of a larger chorus for change. Until our next adventure, I'm Venture, 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 I'm Venture,